Warning, the video you're about to watch contains mathematics at the level of integral calculus, also known as Calc 2. All material has an assumed prerequisite of differential calculus and a full semester course in trigonometry. A thorough review of prerequisite topics can be found by searching the web.
It's the system of equations. We must deal with them all at once. Always looking for solutions. Positive outlook overcome.
Hello, my name is Roy Simpson, Professor of Mathematics at Cosumnes River College in Sacramento, California. This video is dedicated to Calc 2 students, or students who are currently enrolled in integral calculus, who are just learning about volumes of solids by rotation specifically. And in that process, you're learning how to compute the volume of a solid of rotation using one of two different methods. The first method is called the disk and the washer method. They kind of are glued together. They're sort of the same method. And the second method is called the method of shells or cylinders. I'm going to teach this topic, or I'm going to do this example as if you only know how to do washers or disks. They're kind of the same thing, like I said. So let's go ahead and use that idea to set up an integral for the volume of a solid torus with radii little r and big R, and I'll tell you what that means in a moment. And then, by interpreting the integral as an area, let's go ahead and find the volume of that torus. Now, I sort of shorthanded the language here because I knew what I was talking about when I wrote this down, but anybody who reads this pair of sentences might not quite understand what I mean by those radii there. So let me be a little more specific. We have a torus. A torus is like a donut. A donut that looks sort of like this. Now, you'll have to forgive me, I am not the best artist in the world, or near enough to any artist in the world, actually. I'm really terrible. However, you can imagine that this is a donut formed by rotating this circle about some vertical axis, the vertical axis being right about here. And I'll call that the y-axis, why not? And we also have an x-axis, which is right about here. Now, what do I mean by set up an integral for the volume of a solid torus with radii little r and big R? How can that donut have two radii? Well, what I mean is there are two circles happening here. There are these minor circles, kind of the volume of the donut itself, and that will have a radius of little r, just like that. And that radius is obviously from the center of the circle. And then we have a big circle of rotation about the y-axis. That big circle of rotation will have radius capital R. And there we go. So that's what I mean by radii little r and big R. The circle that you're rotating around has a radius of little r, and it's rotating around the y-axis via a radius of capital R. There we go. And we're going to set up the integral for this volume and then try our best to compute the volume of this solid. Now remember, the only thing I'm allowing us to use is the disk method or washer method. That's the only method I'm allowing us to use here, which is actually going to be the hardest of the methods to use for a solid like this. But generally speaking, this is a problem you first encounter when you're dealing with washers or disks. So let's go ahead and set that up. Conceptually, it's pretty easy to understand. You're just stacking on horizontal plates in this solid. They kind of look like the following. And actually, before I get too far into what they look like, let me start by saying I'm going to do a horizontal slice here. And the horizontal slice I'm going to do, I'm actually, just for notational purposes, I'm going to put the horizontal slice right here. Mainly because it's a little bit messy where my drawing is anyway, everywhere else. And so I want to keep my drawing for my horizontal slice a little bit away from all my ink, just so that you guys can see it. Obviously, if I take that little strip right there and I rotate it around the y-axis, it will create a plate with a hole in it. Right? Or what we call a washer. I like to just call them plates with holes in them though, just because, I don't know, I like to. All right, so that's the slice we're doing. By the way, the thickness of that slice there is a delta y. It's a wiggle in the y value. So we happen to know the variable with which we're going to integrate. To keep my drawing clean, I'm going to go ahead and redraw that plate just down below this picture and then rotate it around a fictitious y-axis so we can see what that volume of that plate looks like. Now, to be very honest with you, this is probably the best disc or washer that I've ever drawn, and it's really terrible, even though it's the best one I've ever drawn. Again, I'm not an artist, but there's a typical washer. That's that washer developed from rotating this thin slice about the y-axis here, just like that. And we know the thickness of it, again, is just a wiggle in y. Now, conceptually, it should be pretty easy to understand how this is going to work. We have a plate which has an area of pi r squared and a thickness of delta y. And if you're one of my students, you know the formulas that I use are very language driven. So in other words, that outer plate, the big plate without the hole in it. So just imagine you had a plate here without a hole drilled out of it. That outer plate would have volume of area, surface area, which is pi r squared, pi r of the radius of the outer plate squared, times its thickness, delta y. So that would be the volume of the outer plate. And what we're going to subtract off is the volume of the hole we have drilled out, which for visuals, I've put there in kind of gray. That's a volume that we will have drilled out. And just like the outer plate, the inner plate has a thickness of delta y. So the surface area of that plate would be pi r squared, where r is the radius of the inner plate. Square that, multiply by delta y, and you have the volume that you're drilling out there. So conceptually, that's the mathematics behind the scenes for the volume of that slice. Not terrible conceptually. However, mechanically, it is a little bit of a bear. And here's why. If you look at the edges of the function, basically what describes the right edge here and the left edge of this slice, so I'll call this x sub r for the right edge of the slice and x sub l for the left edge of the slice, the function that describes both x sub r and x sub l, those are the same functions actually. It's the circle, right? Well, the circle is actually not a function, but it's the top half of a circle, which is a problem. So we need to somehow rewrite x right and x left in some way so that we don't end up subtracting a function from itself. So let's see how that's going to work. Well, let's see. The outer plate, that's pi radius outer squared delta y. So let's go ahead and just say that equals here. Pi, the radius of this outer edge is this distance from the central axis of rotation all the way over to this x right value. So I'm going to call that x sub r squared because that's the x value for the right edge of our slice. That's what we're pretending it is going to be. And of course, we have a delta y there. Now let's go ahead and continue forward with that conversation, because being able to do that will inform us how to find x sub l. And in fact, while I'm here, I'm going to go ahead and grab this language here, and I'm going to move it over to the left a little bit so that we have some room to do the mathematics. In fact, I'm also going to grab this and move that down slightly. All right, so what do we do here? We have pi x sub r squared times delta y. The problem is when you write your formulas, if you know you're working with delta y's, that means all these x values have to be exchanged for y values. So let's go ahead and see if there's a formula relating x and y for this edge right here. In fact, this entire edge right here. The formula that relates x to y along the edge of this circle is, well, I hope you guessed it, the formula for the equation of a circle of radius little r. And we happen to know the equation of a circle of radius little r is something like x squared plus y squared is equal to little r squared, with the exception that this circle is not sitting at the origin. This circle is actually shifted to the right. How many units? Well, this center right here is at capital R comma 0. So the center for our circle is at capital R comma 0, which means we've shifted it by R values, capital R values to the right. So we're going to adjust this X value using all of our algebra from the past, not all of it, but the pertinent algebra for this problem. And there you have it. That's the equation, the actual equation that we're going to be dealing with for the rest of this problem. That is the equation of this circle. What we need to do is we need to obviously solve it for x sub r or x sub r squared. When I say x sub r, I really mean x. We're just going to solve it for x or x squared if we can. So going back to the equation up here, I'm going to go ahead and say this implies that x minus capital R being squared is little r squared minus little y squared. And then I'll take the square root of both sides. And when you take the square root of both sides, don't forget, if some number squared is equal to something else, and you take the square root of both sides, you'll get a plus or minus. And I'll again remind you why in just a moment here. Let me finish writing this out. So why is that true? Well, if I told you that, let's say, some number squared, let's say x squared is equal to 9, when you take the square root of both sides, I hope you understand that x does not have to be actually 3. It could have been negative 3. It could be plus or minus 3. So therefore, when I have some number squared equaling some other number, and I have to take the square root of both sides, I will insert the plus or minus. That's a good old algebra reminder there. Add capital R to both sides here, and there is the relation. Whenever we see an x, we can trade it out for a capital R plus or minus the square root of little r squared minus little y squared. Now, how do I know which of these two things it is? Is it going to be a plus or is it going to be a minus? Well, that just depends, actually. If I am on this edge right here, notice all the x values on that half of the circle, they start at capital R, or near enough to it, I suppose. They start at capital R, and then they increase from there. For example, this x value, the x value associated with that point right there, is going to be slightly larger than capital R, because capital R is the center of the circle. So I highlighted that edge green because it's associated with the capital R plus square root of little r squared minus little y squared. If on the other hand, we happen to be dealing with the left edge of the circle, all of the x values over here, specifically, let's just say this point right here, the x value for that point is going to be at capital R minus a little bit, right? So that's again why I color coded it here. It's going to be capital R minus the square root. So that's how I'm going to know what formula to use and when. Now let's go ahead and take a look at our formula we've been working on here very briefly. We're working with the volume of the outer plate, which is associated with the x value on the right edge of our slice. And the x value on the right edge of our slice, this x value right here, well, that x value, maybe I should make it a little more obvious, there we go, we know is going to be capital R plus the square root of little r squared minus little y squared. So let's go ahead and insert that into our equation. And there we have it. Now let me just double check my formula and make sure I did everything correctly. I did. Okay, so one thing I do want to note here, technically that y should be a y sub I because you're looking at the y value at the ith slice. The capital R and little r, those are constants, like the radius of the donut and the radius of the circle. Well, those are constants. Somebody will hand us those numbers later. We could multiply this out, I suppose. That's actually not a bad idea. So I'm going to go ahead and do that. There we go. Not too bad. I mean, it does look terrible, don't get me wrong, but it's actually not too bad. All right, so I have that set up. Notice that this formula, which is for the volume of the outer plate, the only variables involved in this formula is this y sub I here, this y sub I here, and then that's it, really. We're integrating with respect to y in the long run. So we do not have a mixture of variables. That's good news. We're not integrating something with respect to x and y, or we don't have a function that's a function of x and y simultaneously. It's just a function of y here. Remember, little r and capital R are constants. Now that we have that formula written, let's go ahead and write down a formula for the inner plate. Remember, the inner plate is pi, or the volume of the inner plate, is pi radius of the inner plate squared times the thickness, which is delta y. Now, if I look at the radius of the inner plate, which is this inner plate right here that I'm going to be taking out, the radius to the edge of that, so I'll just do it like this, that distance right there, well, that is actually what we wrote up here to be x sub left. So I'm going to go ahead and say that the volume of the inner slice, or the inner plate, is pi times x left, being squared delta y. Now again, that's a mixture of variables. We can't have that happen. However, I have a formula for the left edge of our circle. Remember the left edge of our circle here, I color coded as red, and anything that was in red, any point that was in red, had an x value of capital R minus square root of little r squared minus little y squared. So let me go ahead and write that in here. And remember, it's y sub I because you're looking at the ith slice here. And because we're only setting up the discrete values for the discrete plates that we're stacking there. Multiplying all this stuff out, we'll get the following, which looks very, very similar to the outer plate volume, right? The only difference being that we have here for the outer plate, we're adding 2r root something, and here with the inner plate, we're subtracting 2r root something. Now, this is a great problem because it showcases that you want to have some patience when you're working through this, and you want to be able to do all this preconditioned work first. You don't want to dive into the integral. You actually want to just find out, well, what's the volume of the outer plate, and what's the volume of the inner plate? Let's go ahead and do the mathematics to subtract the inner volume from the outer volume. Let's do that right now. So volume outer minus volume inner. And what I'll do is I'll distribute the pi's through and the delta y's through so you can really see what's going on. So for the outer plate, I'll distribute the pi and the delta y through to each of those 4 terms in there. And there we have it. That's just the outer plate, everything distributed. And then from that, I'm going to subtract the volume of the inner plate. Let's go ahead and distribute that pi and that delta y to each of those 4 terms. I'm going to pause right here. I want to showcase something. Remember, we're subtracting each of these terms here. So subtracting the pi r squared, well, that's just a minus pi r squared delta y. Subtracting the negative 2r times pi times square root, well, that's going to be a positive. That's where I got that positive from. That's why I wanted to pause and take a moment to showcase that. Anyway, continue the subtraction of each of those terms. And you can see why I recommend pre-working all this without an integral. This is all good old algebra, and you notice what happens. I hope that you notice what happens here, that this pi r squared delta y cancels with this negative pi r squared delta y. This pi r squared delta y cancels with this negative pi r squared delta y. And then finally, this negative pi y sub I squared delta y cancels this positive pi y sub y. It's hard for me to say. Pi y sub I squared delta y. So those expressions cancel each other. The only thing that remains actually after you take the difference in volumes is this 4 of these pi capital R root little r squareds minus little y sub I squared and then a delta y. It actually compresses down very nicely to just that. That is the volume of the ith washer. Now what we're going to do is go ahead and take that volume of the washer there, and we're going to integrate it. We're just going to add up a bunch of washers. Now to do this, I want you to draw your attention to the fact that there is a little bit of symmetry going on here. I hope you agree that the top half of this donut should have the same volume as the bottom half. So that top half right there should have the same volume as the bottom half down here. It really does actually have the same volume because it's symmetric, right? So all I really want to do is start stacking plates, not from negative little r to positive little r. I want to start stacking plates at 0, at a height of 0, basically right here. That's where I want to start stacking plates, and I'll finish stacking plates when I get to the top, and then I'll double up that volume. So let's go ahead and set up the integral. So let's go ahead and do that. I'm going to set up my integral. Again, I'm going to stack plates, so the true volume. I'm I'm going to stack plates starting at a height of 0 and ending at a height of little r. This distance right here in y value is actually a distance of little r. And that means I'm going to, in the end, double up my volume because I'm only actually stacking plates only in the top half of the donut. And I'd like to double that up to get the full donut in the long run. And we have 4 pi capital R and then square root of little r squared minus little y squared dy. Now, if you look at that and you think about your integration techniques that you've learned so far within calculus, if you have not learned anything other than basic integration and substitution rule, then you cannot technically integrate this analytically. However, if you're one of my students, then you should know that there are other ways to evaluate an integral, specifically thinking of this as a geometric object. Now, to do this, you have to let go of the donut picture for a moment, because you're going to want to kind of grab onto that donut picture and hold on to that for dear life, thinking that that's the picture you're actually integrating over, but it's not. You're actually finding the area, if you will, underneath a completely different function. So here is the function with which you are finding the area underneath, specifically this guy right here. If I take a look at that function, just forget about the donut, forget about all that conversation for right now, and just say, well, what is a geometric interpretation of x equaling the square root of little r squared minus little y squared? Well, if you square both sides, you would get x squared is equal to little r squared minus little y squared. And if you add little y squared to both sides, your geometric interpretation here is that you have a circle centered at the origin of radius little r. Here's my circle centered at the origin of radius little r. It's not the best circle, I just want to chicken scratch that out. And I want to find that area for the positive x values, right? Notice this is positive square root, not negative square root. So I want to find the area of this region here. And if you take a look at that region right there, that is part of a circle of radius r. Specifically, we want to find the area from y equals 0 to y equals r, where x is positive. Let me just showcase what that is. It's right there. Wouldn't you agree that all the y values where I've highlighted are positive, or non-negative, I should say, and all the x values are also non-negative? And what is that area? Well, it's the area of 1/4 of a circle. And that circle has radius little r. So the geometric interpretation of this integral is this is the area of 1/4 of a circle of radius little r. Cleaning that up, we get our final answer that tells us the volume of that donut, of that torus, is 2 pi squared little r squared times capital R. If somebody walks in, they say, I have a torus that has a small radius, or I guess this little radius right here of, I don't care, 1 inch, and the donut itself from center to middle of dough, it may have a radius of 2 inches. Then I can just plug those values right into this formula, and I can tell you the actual volume of that torus. Now, if you have already gone through the shell method, there is something very similar that you can do to find the volume of this torus using shells. I'm not going to do it in this video because this video is really meant for you as you're learning the disc and washer method, in order to show you that you can find the volumes of these types of things, but it is a little bit of a pain. And the trick in this case really was to note, I have 2 edges on this circle. One edge right here, where my x values are greater than or equal to capital R, and one edge right here, where your x values are less than or equal to capital R. And so that tells you which of these 2 functions x is equal to. All right, that's a very big problem, or example, I should say, that often students face when they first learn this material, and it can seem confounding, but it's a great exercise in how to set up integrals. And also, it's a wonderful exercise so that you can recall, oh, you know what? I can just use my interpretation, my geometric interpretation of what this function really is to help me evaluate the area underneath that curve. Specifically, that's just 1/4 of a circle, and I can easily compute that without calculus. All right, despite that being kind of a complex problem, I hope it was helpful, and I will see you in a future video.
It's the system of equations. We must deal with them all at once. Always looking for solutions. Positive outlook overcomes obstacles getting in our way. Cause affects more than we can sometimes see. Things for what they are and work together until you feel at peace. Says, listen close. Don't talk too much that isn't kosher. You may really hurt inside. It doesn't justify you to speak too loud and cry.